Coming up on this edition of the FRC Open Alliance Show, 8324 MECO Robotics from Florida is in to really catch us up to speed on everything they've been working on. We jump into their game strategy a little bit, but really hitting hard into their robot design, where they're at so far in regards to CAD and showcasing some prototypes as well. They're doing something really interesting with a dual intake approach for the Coral this year and showcasing how they're looking at scoring with kind of this fork interesting design that they're using for level 4 scoring as well too. So a lot of great stuff with that. We're talking about some of their custom machining and then jumping into some of their auto routines and pathing, what they're looking at doing for that. We'll walk through a couple different autonomous strategies that they have in mind as well. So let's learn more about MECO Robotics coming up here on the FRC Open Alliance Show. Let's welcome on 8324 MECO Robotics coming in from Florida. They're competing weeks 3 and 4, and we can't wait to jump into all the awesome topics and progress that they've been working on so far. So welcome, students. If you don't mind, can you introduce yourselves? Let us know what you do on the team, and we're going to hop right into some of your game design and strategy.
Yeah, so I'm Nate. I'm the lead programmer on the team.
I'm Lily. I'm the team captain and the media lead.
I'm Aaron. I'm one of the designers.
And I'm Mason. I'm the mechanical lead for the team.
All right, so we're going to go ahead and start off doing a little intro for our team. So we are MECO Robotics. We are a 5th-year team. We started right at the beginning of 2019. That also means our first season was 2020. We were in the unfortunate situation of where the Orlando Regional was our first competition. So we were on the field for the drivers meeting, and that was when they had to send everybody home. So that was unfortunate. We switched online for about a year and a half before we started meeting back in person. And now we are located at Orange County Academy in Bithlo, Florida. Bithlo is kind of an underserved part of the East Orlando community. Very poor infrastructure, not a lot of, there's no place to earn, there's not many places to earn a GED. There's not many job opportunities or anything like that. So our goal with being here and running our FRC and our FLL team is to kind of provide a STEM outlet and a light in the community that didn't really have that before. So last year we had our best record year yet. We competed at the Orlando Regional, placed 12th, and we captained Alliance 7. That was also the first time we were ever Alliance captains in our team's history, which was awesome. Some other stuff notably that we've done is we went to the West Virginia Robotics Extreme this past off season. That was super fun, so we got to travel up to that. And then we'll be competing at the Orlando and Tallahassee Regionals this upcoming season. So moving past onto that, I'm going to go a little bit into our robot design and kind of how we decide on what design we want to focus on for the year. So for the past season and this season as well, we compile a Moscow list at the beginning of the season, which a lot of teams do. And it's basically must have, should have, won't have. And so basically we go through a list of what abilities we want the robot to be able to have, basically. So obviously our number one on must have is swerve drive. That's a mandatory. We definitely absolutely want that. All the different scoring elements that we want to be able to complete. And then we rank those on a 1 to 5 scale based on our team's unique abilities for that year. So the manpower we have, the materials we're going to have, be able to access, our budget, different things like that. We basically filter through everything possible that we're able to complete in a game and then choose our abilities based on that Moscow list. So now I can pass it over to design and some of the decisions we made.
So this year we're going with a lot of the designs we've seen so far, which is the main part of the robot being the elevator. And we have some requirements for those designs. The main for the elevator is having a low center of gravity, low chance of tipping, and also be able to have our torque still kind of high. It's having it semi-lightweight so that we can still remain our weight down. Having a low part count. A lot of elevators are very complicated and have a lot of parts that need a lot of manufacturing. That also increases complexity. We wanted to keep that low. And then having a sub 1 second to full extensions to be able to score L4 as fast as possible without being the bottleneck of the robot. The way we're doing that is having a 2-stage elevator that is about 2 inches below the height limit. It uses a HTD belt internally run through the box tubes. It's 2 of those, and it's a 2-motor gearbox, and it runs those through the box tubes to be able to keep the profile of the elevator low while still maintaining rigidity. And with using Kevlar belts, they often fray and break, so it makes that a lot more rigid for the elevator. Moving on to the next subsystem, we have the arm. The arm goes on the 2nd stage of the elevator. The main requirements for that was being extremely lightweight so we could still keep that sub 1 second for the elevator. it was easily manufacturable. We have some limits we'll talk about later. And we want to be able to replace the arm if need be, and also iterate. And then the other one is being a sub 1 second to full rotation, so that when we have coral, we can still reach L4 and that not being the bottleneck. The way we did that is using a carbon fiber tube we have here. We use this, we got it donated from rowing oars, and we cut them down so they remain extremely lightweight, being very cheap because they were donated, and very strong and very rigid. We have, for the main gear and for the main arm, we have a herringbone gear that was 3D printed. So this is extremely easily manufacturable, and we can recreate it while also being able to be iterated if need be. And if it breaks, we can remanufacture it. And that uses 2 polycarb plates for a lot of rigidity. And then we also, for the mounting of the tube, we have 3D printed 2 mounts that clamp the tube. Those are custom, and those enable the arm to be very rigid still at the bottom and at the top for the end effector. Moving on to the next subsystem, we have the intake. We decided to go with an intake this year. It enables us to get a little bit closer to the reef without having to go all the way to the human player station. We'll talk about that strategy a little bit later on as well. The requirements for that were being full width so that we could take in coral from 2 sides of the robot and use the whole side of that. We wanted it to intake coral from essentially any point when the coral is laying down on its side, and we don't have to worry about orienting the robot around the coral. And then touch it, own it, so that when we get near the coral, we can immediately put it into the robot. The way we're doing that is using a 4-bar intake to maintain that low vertical profile when it's stored in, while still being able to deploy out far enough to be able to reach coral where it would be hard to get otherwise. And it centers to the front of the elevator, and the elevator the arm grabs it and then can raise the whole elevator. The next subsystem we have is the drive base. The drive base is a little bit unique this year. A lot of people have been going with unique designs. This one we thought of actually before the season, and it worked perfectly for this season. This season has very little bumps or anything on the field that could get in the way of the drive base, so it enables us to get even closer to the ground than a normal drive base chassis would have. So what we do is, instead of using 2x1 or even 3x1, we use a 1x1 and 2x1 combination with polycarb in between. The 2x1 is on the bottom and enables us to put the belly pan sandwiched in between the 1x1 and 2x1 and put all the electronics facing down. So that keeps our CG low while still making the electronics isolated from the rest of the robot. And we can still mount things to the top of the robot with a lower CG than most 3x1 designs.
Can you talk about your concept of, or your decision making of wanting to go with a square drive base as well too, and how that kind of worked out for your full design?
Yeah. Say that for the square, you said?
Yeah, going with the square drive base. What made you choose with that, or why was that the best or most effective design for what your team decided to go with this year?
Yeah, so in terms of the square drive, so last season we ran our swerve modules in a square, but we also had an intake sticking outside of the frame of the swerve drive for the under the bumper intake. And while that was great in protection of the intake, what we found was the maneuverability of the robot decreased, as now we have to worry about maneuvering a big 6-inch sticking out intake while also maneuvering a swerve base around other robots. So this year we saw that the reef is very close to the source, so it's going to be a game of cycle times. And if we're able to be super fast and super maneuverable, we're able to intake coral faster. And also, even though there is allowed one opposing robot of defense on your side, we realized most of the defense being played this season may actually be our own alliance, where we have 2 sources, but there's 3 robots on your alliance. So trying to figure out how to have 3 robots intake from 2 sources and just figure out how to choreograph that cycles, we found that we may want to be able to maneuver around our alliance partners, and having a ground intake will help decrease our cycle times, as we're no longer having to line up or fight to get fed from the source. We can just pick it off the ground and get out of the way.
One other thing I want to ask you about too, and just go back a little bit, was in regards to your end effector for scoring coral on here. So when you were testing this and creating this, or doing it in CAD, or even with your prototypes on there, what angle did you end up with in order to kind of deliver this? Because essentially, are you putting the coral on those stakes essentially, and then it's sliding off, or how does that process work exactly? And then what kind of angles does that look like for you?
So we've been running through some iterations. This is one of the prototypes we made, and this one is currently passive. And the idea is that it just sandwiches the coral in between without using motors, and it can grab it like that. The issue we found with it is that you would have to put it on the reef and then pull it off, and that would take too long. So what we decided to do was, one of the things we're iterating right now is putting a wheel at the very back to push the coral down. So what that enables us to do is that probably about a 15-degree angle for L4, and instead of having to go down on top of it, we can just shoot it directly down using that wheel. Same with the other ones, we can kind of put the elevator all the way back and shoot the coral out without having to either put it on or some other mechanism.
Very cool. Let's run through a couple other things you want to cover in regards to that slideshow. And then I know we got some great stuff in terms of vision and autonomous and other things you want to go through.
So because our build space is fairly small compared to other teams, that obviously limits our machining and what we're able to do. So the biggest thing that's affected with that is our CNC size. So like we have a really small CNC compared to most teams. It's about the size of the robot, if not smaller. It can only fit about like a 1 foot square in its bed. So there's not a lot we can really do with that CNC. So what we decided to do for a workaround is either outsource those CNC parts and just send out plates to other fellow teams that we can work with, such as 2152 or 2383. And that allows us to still get those big plates around, so we can still buy those big sheet metals, make giant pieces of plate we can cut for our robot, and then we can just have it manufactured pretty easily. And the other thing that's very unique to our team is that we use a shaper, which is essentially like a handheld router, which is like a CNC, but it works really well for polycarb and wood specifically, which allows us to get very like accurate bumper shape, size, and anything we need. If we want to do that, we can put pockets in the bumper if we need to. And it also allows us to do super fast iteration for any polycarbonate components, because we can just whip out the shaper and just immediately handheld route the thing. We can design a part in a day and machine it in a day and immediately test it, potentially that same day if we have enough time. So that allows for super fast iteration. And polycarb, it's also a great material, super flexible. We have a ton of it. We love to use it. Almost every single one of our robots has used it. It's one of the greatest materials, I think, for our team. I love it a lot. And we can also use MDF board for prototyping. So we use for our intake, which is down here, which may not be in frame, but that's okay. It's MDF board intake. So each part is manufactured with that shaper. So we can just manufacture it all in a day and test it and see whether our design is actually working or not, which again allows us to have really fast iteration and actually test those angles and compressions and everything that we need. So, yeah. And then another thing that we got is custom wheels. So we've experimented with custom manufacturing our own wheels, similar to how the Vex wheels work. So instead of having to like buy like tens, not hundreds, but like within 10 to 100 wheels for intakes, because intakes use a lot of wheels, we can just use molds to manufacture the wheels ourselves. And so that allows us to have great customizability over the wheels. Like we can either have pockets like the Vex ones come with, or we can make it solid and just do it like that. Or we can make it an inch wide, maybe 2 inches wide, whatever we want to do. We can also manufacture parts like these. So this is a like WCP grip lock kind of thing. It's this like TPU tread. And what we could do, we're going to try to experiment and iterate on, is using like 90A durometer silicon to fill a mold and then potentially manufacture our own tread if that's possible. We're looking into that, and that might be a great option for us.
Very cool. You know, as we wrap up in here, I never want to leave what you're doing for Autonomous Division now, because there's a lot of great stuff, especially on your Chief Delphi build blog that you've been mentioning as well, too. So let's hop into some of the different pathing processes you've been doing and what you've been all working on from that front.
Sure.
Yeah, so this season at the beginning of kickoff, we looked at the field and we realized vision is going to play an essential part into this robot this year. Because looking at the reef from the driver station, all of the scoring locations kind of clump together, and it just becomes really difficult to figure out and line up your robot to score. So on our competition robot, we have a B-Link mini PC that is going to be running Tag Slam, and then we're running a cluster of Orange Pis to do game piece tracking using the neural network. And then, so shortly after that, we ran some path analysis, where basically we're just saying we ran all of our calculations of how fast a robot would be based on the motors and gear ratios we chose in Recalc. And we're not assuming lineup time, even though we're hoping lineup time would be built into the path with computer vision. But we're going to take that variable out just for simplicity. And we're also going to take out the variable of having to intake. So like right now, we're just solely focused on the driving path. And if you look in the top left-hand corner, that's the path for the source intake. So from the source to the scoring location closest to us, that's around a 1.71 second drive time. Versus from the ground intaking, we watched a video from 8738 where they were basically trying to figure out how far the coral would roll as you like throw it down the chute, or you just let it fall, or you physically force it down the chute. Those rules may change based on the new Team Update 7, based on how far you're able to stick your hand through the chute. But just based on dropping, we'll say give or take 6 inches. And then if you look at the ground intake on the bottom right-hand corner, that's around a 1.46 second drive time. So it's around a difference of 0.3 seconds, which doesn't sound like a lot, but when you're trying to get the Reef RP and you're doing 5 cycles on 4 different levels, that will save you a lot of time. So if we move on to the next slide, and we look at, these are actually mapped out cycles, so we're including driving there and driving back. From the source, we're looking at 3.42 second cycle time, versus the ground, we're looking at 3.92. Again, doesn't seem like a lot, but over time, adding up these differences, it will contribute to a lot of time, and hopefully it'll allow us to be able to get those extra cycles squeezed out and just be as efficient scorers as possible. And then going on to our last slide, or second to last slide, my bad. Here I calculated the 5 closest scoring opportunities for us towards that RP for the Reef. So basically, you can see 5 different locations that we go to drive to score. To score those 5 locations, that's a 14.05 second drive time, and that's just for that's around for just one level, and then we can multiply that by 4 for the different 4 levels, and that would just kind of give us an insight of just driving based perfect scenario. How would that take us to get to the scoring locations? And then going on to our last slide. This is one of our possible autos that we're looking at this season. You can see up in the top, we kind of clump around the source for the ground feeding. But basically, we'll start in the center of the net area, and we'll just rush straight to the center, driving forward. And this auto is 3 L4 scores. So we'll do the top of that one, and then we'll fill up the next 2 closest to us. I think this was around a 13-second drive time without lining up and scoring and intaking, which does seem pretty good. It may be a buzzer beater auto where we'll have to like hope it gets that last cycle off, but I'm hoping we can pull it off this season.
And I'm sorry, I didn't quite catch. Are these all L1 scores then, or are they on different levels?
So for this auto, these are all L4 scoring, but
Wow.
For the path analysis, that was just the pure driving, and we weren't worrying about scoring or intaking. Just to kind of give us predictions of how, like in a perfect world, how fast can we get to that scoring location, and then we can analyze our actual driver driving that path versus the perfect scenario case.
No, I love all the thought process gone into this. MECO Robotics, been really cool to have you on. Make sure you're following their Chief Delphi build blog for all their updates they've been doing. They're competing weeks 3 and 4, so we can't wait to see how you do. You still got a little bit of time to get there, but I know the time crunch is real on that too. So we can't wait to keep following your progress. Thanks a lot, and good luck the rest of the way.
Thank you.
Thank you so much.